Okay, so I'll be broadly giving some introductory lectures on convex optimization, and most of the material, at least the one that I'm going to cover in this, the first lecture can be found in this book called Lectures on Convex Optimization. By Nesterov. Okay, and in this first lecture, okay, so I hope to cover first order gradient based optimization. So let me call it gradient based optimization. And in particular, we'll cover two algorithms. One is gradient descent. And the other one is Nesterov's accelerated gradient descent. This was accelerated gradient. Okay. Okay, so let me start by setting up the framework of what we are going to look at. So in general, optimization involves, let's say, minimizing a function subject to some constraints, but for simplicity, let's just consider unconstrained optimization problems where x, let's say, lies in some n-dimensional space, and we would like to minimize a function f, right? So as the title suggests, we are going to consider convex optimization because it turns out that one, it seems to have a very nice structure, so actually we are able to say very non-trivial things and do a lot of interesting things for these convex, class of convex functions. At the same time, there seem to be quite a few applications, and it has found applications in problems in like several different domains. So the first assumption that we will be, is that f is convex. So in particular, we will be looking at minimization of functions which satisfy the following definition. So where this is the gradient of the function. I mean, there is also another well-known definition of a convex function, which is that f of any convex combination is less than or equal to the convex combination of the function values, right? And it turns out both of these are actually equivalent in some sense, but for this talk, we'll just consider this definition. We'll assume that the function has well-defined gradients at every point, and then we will just consider this definition of the this definition of convexity. So f satisfies this property, right? Yeah. Yeah, this is the inner product between. Yeah, this is the dot product. Scalar dot product. Yeah. Okay. So we'll just consider convex functions, and just to start with, I'll give a simple example. And the simple example is just least squares. And to motivate it from a machine learning point of view, so if you look at, let's say we are getting data points which are of the form AI, BI in RD cross R. And we would like to fit a linear model. What that means is that we wish to find a W such that W transpose AI, the inner product of W and AI, is able to predict this BI well, right? So then the function that, okay, so let's call that X. So the function that we are considering is, so if we are given n data points, So this is a very simple example, which and it's actually a simple calculation to show that f is a convex function in terms of x. So this minimization problem basically turns out to be equivalent to finding a linear model for being able to predict BIs given the AIs. So we have some data and we would like to learn this linear model, which will then be helpful for us given a new AI to predict what the corresponding BI is going to be. Okay. Okay. So the assumption that we made was on the function. The second thing we need to answer is how do we have access to this function, right? So the simplest way, okay. So the very special case would be that we know the full form of the function in some parametric class, but in order to make it more generally applicable, what we can in general assume is only that if we give, we have access to an oracle, which if I give you an x, for example, it will give me, say, the function value, right? So this is called the zeroth order oracle. So a zeroth order oracle, given an x, it will output f of x. And this is one way of having access to a function. Okay. In this case, for example, if I give you an x, we can easily compute what the function value is. So we can actually implement these kind of oracles. And a first order oracle is something where if we input an x, it will give us the gradient of the function. And perhaps also the function itself. Okay, and we can define like second order and in general like pth order oracles and so on, right? Where for any given x, we get the pth order all the way up to grad f of x and then f of x. Right. So as we have access to more and more higher order oracles, it seems like we are getting more and more information about the function. So we should expect that we should be able to optimize functions much better if we had access to higher order oracles as compared to lower order oracles, right? But at the same time, the cost of implementing, say, the higher order oracle might be quite expensive. So in general, there are two parts. So one is complexity of implementing an oracle, and there is complexity of optimization given the oracle. Okay, and it seems like there is some kind of trade-off, because if we assume like higher and higher order oracles, then implementing this is a little difficult. But for the optimization algorithm itself, we have a lot more information, so the algorithm might be able to do something faster, right? And in practice, it turns out that the right balance is achieved between both of them for these first order oracles. The reason for that is there is a theorem which basically says that if our function can be written as a composition of smooth or nice simple functions, then you can actually compute the gradient of the function. So let's say my function is given something like this. So this is x. Right, and I have some combination of these things, and eventually I get f of x, right? As long as each of these components are, so each of these could be addition, multiplication, whatever, some simple manipulations. As long as each of these is kind of simple enough, then the amount of time you take to compute the function itself is, say, linear in the size of the network. It turns out that you can actually compute the gradient of this function as well in only 2 times the size of the network, right? So you can actually, so if you have explicit way of representing a function in this form, then we can actually compute the gradients with only a constant times overhead as compared to computing the function itself. Okay, so the cost of implementing these kind of oracles is pretty much no more than the cost of implementing a 0th order oracle. So a lot of work has gone into understanding what is the best we can do with only first order oracles, where the way we have access to a function is through its gradients. So we give an x and then out comes a gradient, and our algorithm needs to use this gradient information to figure out what is the minimizer of the function. Okay.
But the second one will also be like similarly again a constant times.
It will not be a constant times. I mean, if you
I mean, because the gradient flows, you have the network and it cannot be constant.
no, it's not constant times. I mean, even the output itself, for example, this can be linear. Okay, so just think about it. So grad f of x is the linear in the dimension, right? And a linear in dimension is actually a lower bound on just computing the function value itself, because you have to go through all the bits of the input, right? Whereas when you go to grad square f of x, its size is already d square, d cross d. So that automatically means that you really have to do more work to compute the Hessian as compared to computing the gradient. Okay. Okay. So all of this was just to convey why people have been looking at gradient-based algorithms all that much in machine learning. And the main reason is because computing the gradients is not really any more expensive than just computing the function values. And it turns out that we can still do optimization fairly well even with just the gradient information. Okay. Right. So the simplest kind of algorithm that uses only the gradient information is the gradient descent algorithm, where we start with an x. So the algorithm is this. So this thing eta t is called the step size, or learning rate. And so we start with some point x0, and then at every iteration we look at the gradient at the current point, and then we take a small step in the direction of the negative gradient. Okay, and I guess like the intuition for this is just that the gradient is actually the direction in which the function increases the maximum, and so the negative is the direction in which the function decreases the most, and so we are just stepping in that direction. And we would like to understand the performance of gradient descent and whether it is indeed an optimal algorithm for minimizing convex functions under various assumptions. So before so ideally what we would like to say is, we would like to say that after running t steps of say gradient descent or in general any other algorithm, so what is the bound that we can get after running t steps of gradient descent, right? So in general, this will be a function of t, and also some problem parameters which depend on the function itself, right? We would like to understand what is the best we can say about gradient descent after we run say t steps, or in general any other algorithm. How does so this basically denotes the convergence rate. How does the error that I can guarantee, okay, so this is just, so this is the optimum, and we are just measuring the suboptimality with respect to the optimum, and I would like this to go to 0 as t goes to infinity, right? And the question is at what rate does this go to 0, right? As t goes to infinity, what is the rate at which this goes to 0? How does it depend on the function parameters, and how does it depend on the number of steps that I have taken? So this is what we call convergence rate for any given algorithm. Okay. So in order to say this, we need to consider classes of functions, and then we'll be able to say something about if the function f is chosen from this class, then we'll be able to get this convergence rate, and if it's something else, we'll get some other convergence rate and so on. So we have already assumed that the function f is convex, but we'll need to assume a little more in terms of its local properties. And the simplest assumption that one makes is the following, and then we'll say a theorem. So if f is convex and G Lipschitz. So G Lipschitz just means that right? So this gradient descent. So it may look a little complicated, but it's not that complicated. So on the left-hand side, we have some weighted average. So eta I correspond to weights, and then we are taking a weighted average. So 1 over summation eta I, right? So we have a weighted average of the suboptimality of the ith iterate of gradient descent, right? So that's the left-hand side. So we are getting a bound on the weighted suboptimality of each of the gradient descent iterates. And this is the bound we have gotten, right? So there are two terms in the bound. So one is the distance to optimality of the starting point, right? x0 minus x star square. This is the distance to optimality of the starting point. And the second one has a quantity which depends on the Lipschitz parameter of the function that we are considering, right? And this eta I is actually under our control because this is a part of the algorithm, and we can choose eta I whichever way we want, right? And we can actually choose, say, so let me call it Remark. So if we choose eta I is equal to like a constant which depends on t, right? And we choose it to be So we'll choose all the eta i's to be exactly the same, which is norm of x0 minus x star divided by g square root t, right? And then we just plug this in here. Sorry? No, I don't know X star, and the algorithm is not using X star either. Oh, in this one, so it turns out usually you assume that the X star lies in some ball, and then you would run this algorithm with that particular parameter, and if it does not work, maybe you will double the thing and then run it again. So for theory people, when you are trying to get bounds, usually you don't worry about these issues, but when you actually implement these algorithms, this is indeed an important issue, and there has also been a lot of work on trying to design like parameter-free-ish algorithms where you don't want to assume, for example, like you don't know G and you don't know this, so you would ideally want to design algorithms which automatically adapt to the structure of the problem, but I think the answers there are not like very clean, and it's still kind of open to a lot of questions there are still open. Yeah.
I'm not sure I understand something. You made no assumption of the second derivative of f.
No, I have not made any assumption.
Yeah, so f of x could be in one dimension, f of x could be x, and then there is no minimum.
I mean, okay, so I'm assuming the existence of some optimum x star. So I'm only comparing to that particular comparator. So so this x star, I mean, first currently I'm assuming that x star is a minimizer, right? So it means that a minimum exists, but so it actually is not required. So x star could be any arbitrary point, and this result is true. So in your case, if you keep running the algorithm for long enough, you'll just keep going down and down, right? And after t iterations, you will be definitely better in suboptimality compared to all the points which are only square root t distance away from where you started. So that's how you can read this. So in your case, if you start at 0, then after 3 iterations, your suboptimality is bounded with respect to all points which are in the radius of square root t around the starting point. Yeah.
What's the last factor? RHS 3 was the last factor.
G. Okay, so let's try to prove this theorem. So usually we use some potential function to argue that we are making progress in something, right? So the potential function for this is just xt plus 1 minus x star square. So this is, so the norms here are all Euclidean. There are other things we could do for non-Euclidean norms, but for now, all the norms that I'm using here are Euclidean. So right? And we can just expand this. So this is just expanding the square, and so this is less than or equal to so this term is by convexity. And this term is due to the assumption that the function is Lipschitz. Right? So the convexity of f is something we are applying at xt and x star. So we know, so in particular, this is because f of x star is greater than or equal to f of xt right? So this inequality is just because of convexity of f. And okay, so for Lipschitzness, we have assumed that Lipschitzness means that the function does not change by more than g times the norm of x minus y between 2 points x minus y, x and y. And this is actually equivalent whenever the gradients exist to the gradients being norm bounded. Right? And that's basically what we have used here. Okay, so we can basically take a telescopic sum because xt plus 1 minus x star and xt, so they occur in every term with alternating signs. So, okay, so let me maybe just. So rearranging we get and telescopic sum. So this is always a positive term, so I can just ignore this. So I still have less than equal to. Okay, so this is this proves the thing. Okay. So in particular, if you want to write this, write the optimality result. Okay, so there may be two things that I need to mention. So firstly, we are getting a weighted average of the suboptimality, right? If we are able to indeed also evaluate the function value, it means that the minimum of these also satisfies this bound. So I can indeed get a point which satisfies this suboptimality bound, right? I just look at all the iterates of gradient descent and I pick whichever has the minimum function value, right? That satisfies this bound. The second thing is I don't actually need to compute the function value either, because just by convexity, using the other definition of convexity, you can actually argue that the weighted average, so f right? So I can just take a weighted average of all the iterates that I have seen so far, and I don't even have to store the minimum and so on, right? So this indeed gives not for xt, but at least some kind of weighted average, I get a convergence guarantee. And in this case, it turns out that the convergence guarantee that I'm getting is of this form. Right. So the dependence on the function itself is captured by these two quantities, the Lipschitz parameter and then the distance to the optimal point. And as t goes to infinity, the way this goes to 0 is as 1 over square root t, right? And this 1 over square root t is called the convergence rate of the algorithm for this function class. Okay, yeah.
This whole thing we didn't use at all, as you said before, that the fact that x star was a weakness.
Yeah, this is actually true for any point.
So that you run this and you.
So if there is a minimum, you will converge to that. If there is no minimum and like you can keep decreasing the function, you will just keep decreasing it.
But even if there is a minimum, I chosen this thing x star not to be the minimum. This proof is still valid.
This proof is still valid, but it does not mean that you converge to x star. All you're saying is that your function value will be better than whatever point you're choosing. So the best thing for you to, so this does not really mean that x is converging to x star, right? So that's not what it means. So there is no contradiction.
By saying better,
No, I mean if the function is very flat, right? So there are a lot of points that achieve the same function value, but
It's like this.
Yeah.
Nice minimum.
Yeah.
Apply this proof to this one.
then it does not give you anything strong is all it does, but there is no contradiction. So do you think there is a contradiction or?
That's the thing. I'm saying, where do you, here, you.
Yeah. So all this is saying is you definitely get to whatever is the best possible, but it does not, I mean actually,
This is like for any x star, but it's only interesting when you choose.
yeah. Actually, I mean, this point is very important because there is a subfield called online convex optimization where actually the function, so you do this same thing, but it's just that the function is actually not one fixed function. Every time you are getting a different function. And somehow you want to, so this is something like doing something online. So you see a function and you want to do well with respect to that. And on the whole, when you see all the functions, you want to do something which would have been good had you known all the things a priori, right? And precisely this observation actually tells us that this kind of algorithm will be optimal even for those settings where the function need not be fixed and the same every time, but it could actually vary from time to time. So maybe we don't have to get into it right now, but there is a subfield called online convex optimization which crucially relies on like your observation. So I'm assuming the function is convex, so all local minima are global minima. This is for convex optimization. I mean, this does not apply for non-convex optimization. This is only for convex optimization. Okay, so we see that for at least the class of Lipschitz functions, we are able to get a 1 over square root t convergence rate for gradient descent. And in general, we are interested in not just understanding gradient descent, but also the best possible algorithms, because if gradient descent is not the right thing to do, we would like to see what is the best that we can do with just these oracle models. And it turns out that for the class of Lipschitz functions, this 1 over square root t is indeed the optimal convergence rate one can hope for with any algorithm whatsoever. So okay, so I'll not go into the details, but I'll just mention like the main theorem statement. So there exists a distribution over a class of functions f such that every f in f is G Lipschitz convex the minimizer x star for every f. So let me call it x star of f, right? Given a function f, there exists a minimizer corresponding to that function, right? X star of f satisfies and any randomized algorithm which can access the function f only through the gradients only through the gradient oracle satisfies actually I should say so given any parameter t, any parameter g and any parameter r, because these are the three things that appear in this bound. So where r is like I'm looking at the distance to the optimum. So I'm given all of these three parameters a priori, right? So given the number of iterations that I'm going to run, right? G is the Lipschitz constant of the functions that I would like to consider, and r is the distance that the optimum can lie from my starting point, right? Given these things, given these three parameters, for every parameter, for every value of these parameters, there exists a distribution or a class of functions, capital F, such that all the functions in this class satisfy the properties that we have assumed in this proof. Every f is convex, it's G Lipschitz, right? And the minimizer for each function lies within a small ball, right? Which is bounded by R. And the theorem statement, what it says is that you use any randomized algorithm, not necessarily gradient descent. You can use any algorithm whatsoever. The only restriction is that the only way it can access. Okay, so when I'm saying a distribution, so according to this distribution, we pick one function at random, right? So we pick one function at random. And the only way this algorithm can access that function is through the first order gradient oracle. So the only way it can access the function is it gives a point, and then the gradient oracle returns the value of the gradient. Under this model, any randomized algorithm, it can do whatever it wants with the gradients that it has acquired so far. Any point that it outputs has to, so there is again this multiplication. So I'm taking an expectation with respect to both this distribution which I'm using on the function class and whatever randomization that the algorithm itself can have, right? The suboptimality of the iterate that the algorithm is going to return has to be at least gr over square root t. And this matches the upper bound that we got here up to only up to constants. Okay. So what this is saying is that if all I tell you is that the function is Lipschitz, the function is convex, and maybe there is a bound on the distance to the optimal point, then the rate achieved by gradient descent, which is this gr over square root t, is the best possible without either further assumptions on the function or without having more access to the function, like in a way which is better than the gradient oracle. No. This is saying any randomized algorithm.
It's the expectation of the at any time, right? So
Actually, exact t is not necessarily like the algorithm can return whichever point it wants to return. Okay, so actually this can also be made into high probability. This is actually an information theoretic argument, and you can show that you get, yeah, you can also make it into high probability. Yeah, so this actually, you can construct these things explicitly. This distribution over this class of functions, so given any of these things, we can construct this function class explicitly. And it's basically that there's a lot more information that you need to know about the function class to actually be able to determine what's the optimum point. Whereas the gradient oracle returns you only like a little bit of information at every time step. So you need at least so many queries to actually figure out what's actually the optimum. So that's basically the way the argument goes. Yeah.
With the theorem, you can set the function where you can create an algorithm that is faster than 1 over square. Because that would be outside the middle is set and there is a
Yeah.
it's outside the distribution. Can I come up with an example where it was not out?
So then you are asking about like specific functions, right? So if you give me a specific function, yeah, people can definitely optimize much faster. So also like here, given t, I would, for example, choose the dimension here to be somewhat larger than the number of iterations that you need to run for, right? Once you are allowed to depend on the dimension, so this does not depend on the dimension of like the underlying space. That's actually an important point. Because in practice, like we are working in large dimensional problems. So we would like to minimize the dependence on dimension as much as possible. And this one does not really explicitly depend on the dimension at all. It only depends on like the Lipschitz constant and then the distance to the optimum, but otherwise not on the dimension. So if you're allowed to depend on the dimension, you can actually use ellipsoid method, interior point methods to get like 2 to the minus t kind of rates, but they would depend on the dimension. And I'll get over that limitation here by, given a t, I will choose the dimension of these things to be larger than t. So polynomial in the dimension will actually be comparable to the t. So it will rule out those kind of algorithms. No, it's the same theorem. Okay, so yeah, actually it's the same theorem. So the one that's more popularly known from like the original papers is for deterministic algorithms, and also deterministic algorithms with some more conditions, which still captures gradient descent but not any randomized algorithm. These things have been clarified only a little more recently. Okay, so we saw that if we don't make any more assumptions on the function, then this is indeed the best possible we can get. So we'll go just a step further and assume something which is stronger than Lipschitz's condition, and then see what we can do with that. Okay. Okay, so earlier we assumed, yeah. Yeah. Okay, so earlier we just assumed Lipschitzness of the function. Now let's assume something slightly stronger, which is called smoothness. And smoothness is just that the gradients are Lipschitz. Okay. So we would like to understand again for the gradient descent algorithm, if in addition to convexity we assume that the function is smooth, what is the convergence rate that we can get? Okay. Before we go to that theorem, so let's prove a useful lemma. So if f is L smooth, then given the gradient, we can actually construct a quadratic upper bound for the function. Okay. So the proof of this is as follows. So by the fundamental theorem of calculus, we know that f of y is equal to f of x plus right. So I'm drawing a line between x and y, and I'm just integrating the function from x to y. And if I add that to f of x, I'll just get the function value at y, right? Okay, so this again can be written as, so if I compare this to this thing, so first I can add and subtract this term. Okay. So let me call this script t for term. So t is less than or equal to by Cauchy-Schwarz. And by using smoothness, we can upper bound this by L times the norm of x minus y. Okay. So if you know the gradients are Lipschitz, then the function satisfies this property, which basically means that at a point x, if we construct a first order Taylor approximation to the function and then add a quadratic term, then it actually upper bounds the function globally. That's basically the content of the theorem. Okay. So let's now write the theorem which gives us the performance guarantee of gradient descent for smooth convex functions. Okay. So the difference from the previous theorem that we had is that as t goes to infinity, this goes down as 1 over t as compared to the 1 over square root t we had in the previous setting. Okay. And here L is the smoothness parameter that we assumed in the function, and x0 minus x star is again like the distance to the optimality of the starting point. Also, this is for appropriate step sizes. We'll explicitly say what the step sizes will be as we go through the theorem proof, as we go through the proof of the theorem. Okay. Okay. So we actually proceed in the same way as we did for the previous setting. So we'll again consider the same potential function. So the step size here, let's just say it's some constant. So using the same previous argument, we can say that this is less than or equal to minus okay. This again we got by using convexity, and then this is the norm square of the gradient. So earlier in the previous proof, we just replaced this with a constant square because we just assumed the Lipschitz condition. Here we can actually, because the function is smooth, we can actually say something better about the gradient of f at xt. And the reason we can say this is if you look at the function value, okay, so x star is the optimizer, right? If x star is the optimizer, f of x star is indeed less than or equal to f of xt minus eta so let's say 1 over 2l okay. So x star is the minimizer, right? So the function value at x star is less than the function value at any other point. So let's just consider the function value at xt minus 1 over L grad f of xt. Okay. Now let's use this smoothness lemma. So where I set y is equal to xt minus 1 over L grad f of xt and x is xt. Okay. So just using the lemma where I set x is equal to xt and y is equal to xt minus 1 over L grad f of xt, right? So in particular, if I combine, so this is again norm grad of f of xt square. So if I just combine these terms and rearrange, this implies that okay. So the norm of the gradient square can be actually upper bounded by something which depends on the function value. Earlier, we just used that the norm of the gradient square is just bounded by a constant, right? Here, we are able to say that if the function value is very close to the optimum value, then the norm of the gradient has to be very small. So just rearranging it, what we get is xt plus 1. So if we choose eta to be 1 over 2L, so what we get is 1 over t sorry, there is this missing constant of 2 here. So if I choose eta equal to 1 over 2L, this just becomes 1 over 2L, right? This is just a constant, and then I sum over all t. Because there is a xt plus 1 on one side, xt on the other side, it just telescopes, right? All I'll be left with is x0 minus the initial term x0 minus x star. And because when I take an average and divide by t, so I have this 1 over t here, and this is the constant that we end up with. Okay. So compared to the 1 over square root t convergence rate that we got in the previous setup, we actually get a better convergence rate, which is 1 over t here. So the question we again ask is whether this is indeed the best possible rate for any algorithm, just with these assumptions that the function is convex and L smooth. And it turns out that in this case, gradient descent is actually not the optimal, and we can get a faster algorithm. And in the next half an hour, maybe I'll try to go over that algorithm. And this algorithm is called Nesterov's accelerated gradient algorithm. So to keep it short, the improvement that you get is that instead of a t here, you get a t square with everything else being the same. So the result is that there is an algorithm which is Nesterov's accelerated gradient, which can actually give you f of x t minus f of x star is less than or equal to, again, I mean, there will be some constant, so I'll just put a O. Okay. There's actually a long history to this algorithm, and like the first method, which was like the first ancestor of this method, is what is called Poljac's heavy ball method. And this algorithm worked only for convex quadratic functions. It did not work for anything beyond a quadratic function. And there was a later result which was due to Nemirovsky and Yudin, which again got basically the same rate, but the algorithm was quite complicated. In particular, it had to do something called plane searches, meaning that the algorithm would boil down in every step, it will boil down the problem to some two-dimensional optimization problem. It will solve that exactly, and then it will go to the next iteration. And the Nesterov algorithm is basically a simplification. I mean, it does not directly come from the Nemirovsky and Yudin algorithm, but it's much simpler in the sense that you only have to take some gradient steps. You never have to solve any two-dimensional optimization problem exactly. Okay, and actually the intuition for Poljac's heavy ball method. So maybe I'll just mention a little bit of the intuition here, and then I'll go to describe the Nesterov's accelerated gradient algorithm, and then we'll go through the convergence proof. Okay. Yeah. Yeah.
So for the first thing we had before we went to smoothness, the step sizes hadn't changed.
Yeah.
Whereas here the step size is fixed.
Yeah, that's true.
You continue, you don't have to adapt.
You don't have to adapt, yeah. And the reason for that is here the step size does not have to go to 0, because somehow the gradients automatically go to 0 as you approach the optimum. Whereas in the previous setting, the gradients don't go to 0 as you approach the optimum, so you somehow have to keep decreasing the step sizes. Right. So if you look at the gradient descent algorithm, right, and take the infinitesimal version of the gradient descent algorithm, you approach a differential equation which is the gradient flow. So where x dot is the time derivative of x, and we are saying it's equal to the negative gradient of the function. So when you take the step size of gradient descent algorithm to 0, you will approach this flow algorithm, right? Now, if you think of what happens actually in the world of like Newtonian mechanics, right? Let's say I have a potential function which is given by f, right? So f is the potential function, and let's say I have a ball which is present in this potential function, which is present in this field, right? So I place the ball somewhere here, and you ask if I just leave it be, then it indeed converges to the lowest energy minimum state of the world, right? But the question is, does it follow this when it moves to the minimum, or does it do something else? And Newton's mechanics actually say that velocity, so the negative gradient is just the force, right? And Newton's mechanics do not say that velocity is equal to force. They actually say that acceleration is equal to force, right? So x double dot is equal to minus grad f of x. But if it were this, because of the conservation of energy, it'll actually just come down, it'll go up, it'll come down, it'll go up. It'll never actually stop at the minimum point, right? But as soon as you have some amount of friction, so where theta is some friction parameter, right? It'll come up, it'll go up a little bit, and then go back, and so on, and eventually it'll settle here. So this is the dynamics that are followed by so these are the dynamics that is actually followed by a heavy ball in the actual world, and the main idea behind Polyak's heavy ball method was, why are we even looking at an algorithm of this sort? Maybe it's actually better to do something like this, because this is actually what actually happens in nature, right? And this is fine when we are looking at it in terms of like the flow equation, when the step sizes are very, very small. But actually when we would like to implement this, we would like to do something with non-zero step sizes, right? And then the question is, how do we discretize this equation? So Polyak discretized this in one way. So let me first say that all accelerated methods do some discretization of this dynamics. And the difference between the original Polyak's heavy ball method and the Nesterov's accelerated gradient in the way the discretization is done. It turns out that one kind of discretization is much better than doing a different kind of discretization. And you can actually see this even in the context of the gradient flow, because there are two kinds of discretizations here, right? So one is that xt plus 1 minus xt is equal to minus eta grad f of xt. This is the backward Euler. I think the notation is correct. Okay, and gradient descent does this kind of discretization. So heavy ball method initially tried to do something like this kind of discretization, and for that reason it worked only for quadratic functions, whereas Nesterov's method can be looked at as a more sophisticated way of doing the discretization, although like the proof that we are going to describe will not really go through this kind of framework. There exist viewpoints which actually make this more precise and formal. Okay. Maybe just one more thing I would like to mention. So this kind of discretization issue also happens for the gradient flow algorithm. So this is gradient descent we have been looking at, and this algorithm is what is called the proximal gradient descent. Whenever you can implement something like this, it's always good to implement this. You'll actually get a 1 over t convergence rate. So even in the non-smooth setting, you can actually get a 1 over t convergence rate if you are able to implement this kind of update equation. But implementing something like this is actually much more difficult than implementing this. So this one is very explicit. This one is not explicit. So in general, we cannot implement this. But if we are in a position to actually implement this, then this is always better than this update rule. Okay, so let's now look at Nesterov's accelerated main ideas of Nesterov's accelerated gradient algorithm and why it gets 1 over t square. So, like whatever we are going to do now does not really follow up on this intuition, but we'll do something totally different. But there are references if you want to understand more in terms of like this viewpoint of Nesterov's accelerated gradient. So the viewpoint that I'm going to talk about is starts from the observation that when we are using the gradient descent algorithm, it only uses the gradient at the current point. even though it has seen gradients at all the previous points, it's no longer going to use any of them in the next step. And the main idea is to keep track of all the past gradients that we have seen so far, so that maybe we'll be able to take a better informed step. And in order to make this precise, so we will define something called estimate sequences. So let's start with phi 0. Actually, I have not described the algorithm, so I'll describe both the proof and the algorithm as we go through it, because somehow it will come out naturally. Otherwise, the algorithm might look very ad hoc. Okay, so we are given a starting point x0. We are given a smoothness parameter of the function, which is L, right? And yeah, so these are the two things that we are given. So phi 0 of x is defined to be f of x0 plus okay, so we'll also maintain two iterates. So x0, and then in the beginning we'll have v0 equal to x0, but then in general we'll have xt and vt. So we'll start with an initial function which is like this, and every time we see a gradient, we want to update the estimate sequence. Okay, so we start with phi 0 of x, which is defined this way, right? And at every time instant, we would like to update the phi t of x as a convex combination of whatever we had in the previous time step, plus this new term where yt is a point where we are going to query the gradient and the function value at. Okay. So this will be part of the algorithm. I haven't still told you where we are going to query the gradient and how we are going to implement the algorithm. But let's now say we have access to the function, the gradient information at some point yt. Then we know that this is indeed a lower bound on the function, right? That's by convexity. And we are going to update the estimate sequence at t+1 as a convex combination of the previous one and then the current bound that we have. Okay. So if we define a little more notation, so let's define lambda 0 is equal to 1 and lambda t plus 1 is equal to 1 minus alpha t times lambda t, right? Then is equal to actually okay. So if we just expand this throughout, we will get a convex combination of like the initial phi0 of x and then all the first order Taylor approximations at points ys, and the corresponding coefficients are just whatever 1 minus alpha u's appear after s was chosen, right? Okay, and just by the convexity of the function, we can actually, we know that, so ys I haven't yet told you, so let's say at every point, I give you the gradient and the function value at some points yt.
And you will tell us what it is.
Sorry, and yeah, I'll tell you where I'm going to choose it later. Yeah. So this is less than or equal to lambda t plus 1 times phi0 of x plus 1 minus lambda t plus 1 f of x. This is just because this is always a convex combination. So whatever is lambda t plus 1, the weight I'm going to put on all of these is just going to be 1 minus lambda t plus 1, right? And we know that each of these is indeed a lower bound on the function. So this is less than or equal to f of x. So, and this is the weight. Okay. Okay, so the main reason that these estimate sequences are going to be useful for us is the following lemma. Okay. So what this lemma says is that I'm anyway going to construct these estimate sequences in whichever way, and I'm yet to tell you, of course, what is yt, what is alpha t, and so on. But let's say I construct these estimate sequences. If after constructing these estimate sequences, I'm able to find an xt such that the function value at xt is less than the minimum value of vt, okay, then what I can say is that this xt is very close to the optimum value f of x star, and the suboptimality is bounded by lambda t times something which depends on like phi0 of x star and f of x star.
And this is for any choice of the y's.
This is for any choice of the y's. Yeah. Yeah. So far, I have not really made any assumptions. This is true. Yeah, in general. So the proof actually follows just from this equation. So phi t of, so let me write it this way. So we are looking at f of xt minus f of x star. We know by assumption we know that f of xt is less than this minimum. Okay, and the minimum is indeed less than or equal to phi t of x star minus f of x star. So phi t of x star is again less than or equal to lambda t plus 1 phi0 of x star plus this thing.
What is the minimum amount of yt smaller than phi t of x star?
This is the minimum, right? So minimum is less than phi t at any point.
Minimum x star was the minimum for f.
Yeah, no, I'm saying all I'm using is the minimum value of this function is less than or equal to the function value at any point.
Don't really need this assumption where the smaller the minimum.
Yeah, we don't need that, but this is how we are going to be able to do. Yeah. All we need is like less than or equal to phi t of x star, but x star is something that we don't know. Whereas phi t is something explicit that we have here, and we know what its minimum is. Yeah. Okay. Okay. So at this point, it seems like maybe it's just manipulations, and we are not getting anywhere. But I think there are two main observations that we need to take from here. So the first one, okay. By the way, so let's first convince ourselves that this is somehow useful, because phi 0 of x star is anyway something that's dependent only on the initial points, right? So this is something fixed, and this is something fixed, and this is the only part that actually changes with t. So as t increases, if you can somehow drive this down, then indeed we are able to make the suboptimality very, very small and go to 0 as t goes to infinity, because this is something that's only dependent on the initial point. So what are the two things that we need to do for this one? So one, find xt such that f of xt satisfies this. And two, ensure lambda t goes to 0 as fast as possible. As t goes to infinity. So these are the two things that we need to ensure, and if we are able to ensure both of these, we can just apply this lemma to argue that f of xt minus f of x star will indeed go down to 0. And the main challenge is to find the trade-off between both of these. So we can indeed make lambda t go to 0 very, very quickly, right? Because we are just saying lambda t plus 1 is just 1 minus alpha t times lambda t. So we can choose alpha t to be, say, a constant, and lambda t goes to 0 exponentially, like geometrically fast, like 2 to the minus t. But then we may not be able to find an xt which actually satisfies this. Whereas if we choose alpha t is equal to 0, then the minimizer is just going to be v0, which is the initial point, and we have chosen the function so that at x0, okay. So f of x0 is indeed equal, right? Because this is a quadratic and this is minimized when x is equal to v0, and we said x is equal to x0. So phi 0 of x0 is indeed equal to f of x0, right? So this is true. So in the beginning we have a point which satisfies this, right? And if we choose alpha t equal to 0 all the time, then we don't have to do anything to maintain this invariance, because xt can be equal to x0 and the minimizer is, this is always true. Whereas we don't make any progress towards this because lambda t does not go to 0. Whereas if we choose alpha t to be constant, then lambda t goes to 0 very, very fast, but we may not be able to keep updating our initial x0 to ensure this invariant. So the trade-off is between maintaining these two invariants so that we are eventually able to find a point which satisfies this. Okay. Okay, so the first observation we will make is that phi t of x will always be of a particular form. So this is true because initially it's a quadratic with Hessian being L over 2 times the identity, right? And every time we are only adding linear terms, we are taking convex combination with linear terms. So the resulting function will again be a quadratic with its covariance matrix being a scalar multiple of identity, right? And that scalar multiple is given by this lambda t L over 2. So this is again a computation that we can show. Okay, so this part is clear. So we are combining a quadratic with a linear term. So it will be a quadratic function. And in particular, the Hessian of the quadratic function will be changed only by a constant factor, right? And that constant factor is given explicitly by the term there. Right? Okay, so the lemma that I'm going to write now is going to tell us what phi t star and vt are going to look like in terms of the previous values of the same things. Okay, so firstly, is there any question why phi t looks of this form? Is it clear? Plus lambda t times L divided by 2 times x minus vt square. So I'm saying that phi t always looks of this form for some phi t star and some vt. And the reason for that is because initially it's of course of the same form, right? Phi 0 star is f of x0 and vt is v0 and lambda 0 is equal to 1. So it's exactly of that form, right? And every time I'm going to update phi t using this equation where I'm going to take a convex combination of like the previous phi t with a linear term, right? A quadratic plus a linear term is again a quadratic with the Hessian being changed only by a constant factor, right? The Hessian of this is L over 2 times identity. So the Hessian of the final thing will also be some constant times identity because I'm only taking convex combination with linear functions, right? So that's why I have some constant times identity. Times identity is the covariance matrix, is the Hessian matrix, and the constant is given by lambda t L over 2. And because it's a quadratic, it can so it can be written as a quadratic around the optimum value plus the minimum value of the function. Sorry? Yeah. With identity Hessian. A scalar multiple of identity. Yeah. Okay. And okay, so now if we agree with that, phi t plus 1 has that form. Phi t also has the same form except for phi t star vt, and this one has phi t plus 1 star vt plus 1. So we can just match terms, and I'm saying if we match terms appropriately, this is the update equation that you will get for vt plus 1 in terms of vt and grad f of yt, and phi t plus 1 star in terms of the previous things. Okay. So if we agree with this lemma basically follows by plugging that form of Vt plus 1 here, that form of Vt here, and just matching the constant terms, the linear terms, and the quadratic terms. So I'll maybe finish in like 5 minutes. Okay, and let's do again this by induction. So let's say at time step t we have xt such that f of xt is less than or equal to this, and by just this definition, this is actually equal to Vt star. So what we are going to do is choose xt plus 1 to be okay. So xt plus 1 is a gradient descent step at yt, where yt is the point where we are acquiring the gradient at. So now f of xt plus 1 . Okay, so by smoothness, this implies so I'll just plug in the Vt plus 1 star expression that I have from there. Okay, so I just plugged in Vt plus 1 star from there, and this is equal to okay. Okay, so it looks a little complicated, but we're going to simplify it in a moment. So firstly, if we choose theta and alpha t such that maybe first let's just choose theta. So choose eta equal to 1 over L. Then theta times 1 minus theta L over 2 just becomes 1 over 2L. right? That's this term. Okay, and so we just want to be able to ignore this term. So we want to choose alpha t square over 2 lambda t 1 minus alpha t times L to be less than 1 over 2L, or equivalently this is less than or equal to 1. Okay, so we are choosing eta to be 1 over L, and then we'll choose alpha t so that this whole thing is less than or equal to 1. Lambda t is already something that's given to us, so alpha t we'll choose it this way, and then we'll be able to ignore the second term, and by convexity what we get here is this is less than or equal to grad f of yt times yt minus 1 minus alpha t xt minus alpha t vt. Okay. So yt, I haven't yet specified how I'll choose yt, and now I'm going to specify that yt is going to be exactly equal to this. So this inner product will be equal to 0. Okay. So what we have shown is a way of choosing an eta and an alpha t so that the first invariant is maintained, that xt is always going to be such that f of xt is less than the minimum value of the phi of phi t of x, right? And so that's basically this invariant. So f of xt plus 1 minus phi t plus 1 star is going to be less than or equal to 0. So f of xt plus 1 satisfies the invariant that we want. The second thing that we haven't yet done is to compute the convergence rate, meaning how fast does lambda t go to 0 if we are choosing alpha t in this form. So this basically gives the convergence rate. So lambda 0 is equal to 1, and we are going to choose an alpha t such that this is less than or equal to 1. And as t goes on, how does lambda t actually go to 0? So this is the only thing that's left now. And because we want lambda t to go to 0 as quickly as possible, we want to choose alpha t as large as possible. So pick alpha t as the largest root of this always exists, because if alpha t equal to 0, this thing is equal to 0, and as alpha t goes to 1, this goes to infinity, so it has to cross 1 at some point. So such a thing always exists, right? Let's say we pick it this way, then let's look at at is 1 over square root lambda t, and we are interested in looking at at plus 1 minus at. This is lambda t. Okay. And by definition, lambda t plus 1 is 1 minus alpha t times lambda t. Sorry, lambda t plus 1 is just alpha. Okay, and turns out that is greater than or equal to alpha t over plus 1. So lambda t plus 1 is indeed 1 minus alpha t times lambda t. And so lambda t minus lambda t plus 1 is just alpha t lambda t. So this step uses the fact that lambda t is greater than or equal to lambda t plus 1. So a square root cancels away, and when we bring this to the denominator, we can at most ignore this, and we'll get alpha t over 2 square root lambda t plus 1. And by the assumption, we are choosing alpha t, so this is actually equal to lambda t plus 1. Right? So alpha t square over lambda t plus 1 is equal to 1. So the square root of that is again equal to 1. So this is equal to a half. So what we showed is that at plus 1 minus at is greater than or equal to a half, implies 1 over square root of lambda t plus 1 is greater than or equal to t plus 1 over 2. Right? Every time we increase it by at least a half, this implies t plus 1 whole square. Right? So instead of a 1 over t, we got this 1 over t square because so at time step t, we are going to decrease compared to the initial thing. Again, like we need to expand this a little bit, but it will be easy to see. The mean convergence rate depends on lambda t, and we have gotten that it actually goes down as 1 over t square as compared to 1 over t in the gradient descent setup. So maybe I'll stop here.